This is Basics of Information, Problem 3, Variable Length Encoding. After spending the afternoon in the dentist chair, Ben Bitdiddle has invented a new language called DDS, made up entirely of vowels, which were the only sounds he could make with someone's hand in his mouth. The DDS alphabet consists of the 5 letters A, E, I, O, and U, which occur in messages with the following probabilities. And we'll leave these probabilities up in some form or another for the rest of working out this problem for your convenience. Here are those probabilities for you. Now, part A of this question is that you're told that the first letter of a message that Ben tries to convey to the dentist is an A. So, how many bits of information is this? So once again, using one version of our handy formula from lecture, the probability of A we know is 0.15. We know our formula is bits of information is log base 2 of 1 over p, the probability. So it's just log base 2 of 1 over 0.15. Now, we'll just outline the probabilities here. For part B, the question is, if we're going to make a fixed length encoding that would allow us to have single bit error detection and correction. So we want to be able to know when there was a mistake and what it really should have been when it's only a single bit. Then what Hamming distance do we need between symbols, distinct symbols? So we can use the formula, which is d minus 1 over 2 is the number of bits you can correct, and you can backwards engineer that. I like to think of it visually sometimes. You know, if you think about all the different ways you could get from 0, 0, 0 to some other symbol, you know, how many different things would you need to have? So if we draw this little red dotted line in the middle here, you know, we can tell what symbols everything is really supposed to belong to if it falls on one side of the line. So the Hamming distance we need is 3. We need to be able to have at least one thing on each side of the line other than the original symbols. Alright, so now we're going to start part C. And in part C, we're asked to construct a variable length encoding using the same probabilities for this DDS language that Ben wants to be able to speak to his dentist in. So we need our probabilities. So for A, the probability was 0.15. For E, probability was 0.4. For I, the probability was 0.15. O, 0.15. And U, it was 0.15. So the process that we want to use, the process we use to create the Huffman trees, is we're going to take the 2 least probable symbols that we can get, and we're going to make a new symbol that has a probability equal to, you know, the other 2 old ones. Either of the other 2 old ones. Sorry about that. So a new probability comes from adding the probabilities of the 2 old ones. So those 2 smallest are O and U, or 2 of the smallest. There's a tie. O and U, add that, and the probability for O or U is 0.3. So if you get to this node up here, you could go down and get O or U. Next 2 smallest are I and A. So again, if we're going to make a node AI, which leads to either A or I, the probability of that one is 0.3 also. So let's do the same thing. Create our AI label up there. 1. Now the 2 smallest are OU and AI. E is still bigger at 0.4. So AIOU, it's going to be 0.3 plus 0.3, probability is 0.6. There we go. AIOU 0, 1. And now the two smallest, the only two left, E and AIOU. So the probability should sum to 1, and it does. So AEIOU is our starting node. So if we go ahead and draw that in there, there's E. And our start node, which is AEIOU. Now the encodings for these, we've got A, if you follow the cursor, is 1, 0, 0. For E, following again, we just go down 1, so it's 0. I, 1, 0, 1. Sorry. For O, it's 1, 1, 0. And for U, it's 1, 1, 1.